Have you ever tried to unscramble an egg? To take a whisk and stir it backwards through your breakfast and somehow end up with a perfectly whole yolk in an egg white? Probably not, as such a thing would be impossible. Now imagine for a moment that you had never even seen an uncooked egg, but had only ever seen them scrambled. Just by looking at that mass of yellowish mush, do you think you could envision what it had once been? We exist in a universe that has been churned, refined, mixed, and beaten. Our brightest minds try to piece together the scramble to figure out what the universe used to be before that first whisk. And luckily for us, thanks to telescopes like the James Webb Space Telescope, we can see the cooking process in progress, captured in light emitted from stars millions, if not billions of years ago. By looking at ever more distant stars, we are seeing ever earlier in the process. But the further we go back, the harder things are to unscramble. We are finding things that throw out our expectations and seemingly don't make sense, leaving us to wonder, what do we really know about the early universe? How did it form? And why is what we're seeing not lining up with our models? I'm Alex McColgan and you're watching Astrum. Join with me today in this supercut about cooking an egg. I mean, the origins of the universe. We'll look over scientists' effort to answer those most fundamental questions and examine some of the strangest evidence that seemingly contradicts our answers. It seems universes, much like eggs, are very difficult to unscramble. When scientists revealed the James Webb Space Telescope's first images back in July 2022, it was a source of great excitement in the astronomical community. The telescope is a 6,500 kilogram monster with a sun shield whose 14 by 21 meter dimensions are around the size of a tennis court. Its mirror for capturing light is 6 times larger by area than Hubble's lens, which allows it to pick up more photons from further away to create crisp images. It boasts numerous cameras and scientific instruments which allow it to see across the infrared spectrum. This is a feature that is vital to its unique mission. That mission is wide in scope. However, one of the things scientists were most excited about was the James Webb Space Telescope's ability to see the most distant galaxies possible. It takes time for light to travel, so if you can see an object in the distance, you are actually seeing it in the past, as it was, rather than how it is. In this way, the James Webb Space Telescope was designed to see the earliest moments possible, collecting light emitted by the first ever stars and galaxies right at the dawn of the universe. Here is an image known as Webb's first deep field. This image is taken from an area so small, a single grain of sand held out at arm's length would block it from your view in the night sky. At this scale, individual stars are almost completely absent. Most of what you can see here are not stars, which would be too small to detect on their own, but galaxies. Here you can see the fish lens effects being created by gravitational warping, as relatively nearer objects bend light around them, distorting what lies beyond. And here we can start to see the edges of the universe. In this image is one of the oldest galaxies we have ever sighted. It is so far away, the light from it, when it was born at the beginning of the universe, has only just reached us. Do you see it? It's admittedly quite small. By evaluating markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus how long the light from it has been traveling by comparing it to normal visible light from similar sources. This tiny dot was found to be 13.1 billion light years away. No wonder scientists were excited. By piecing together data from galaxies like this one, we could begin to investigate what conditions were like back then, and thus how our universe came to be. But it wasn't like we were going into this blind. Long before the James Webb Space Telescope was launched, we had already started formulating ideas about the origins of our universe. Let's start with a question. How old is our universe? You have probably heard that modern-day science believes the universe to be 13.8 billion years old. It seems rather unfathomable how anyone can come to that conclusion, but actually the how is not too difficult to understand. People just don't generally ask the question. Either they scoff at it or they accept it as truth. So how did we come to that figure? It starts with the fact that we currently see the universe is expanding and cooling. Everything is moving away from everything, excluding forces like gravity keeping things together. The speed of this expansion is known as the Hubble constant, and currently the universe is expanding at a rate of 80,000 kilometers per hour per million light years. So, the obvious conclusion from an expanding universe is that matter is becoming diluted. There's more space in between things. This led to an observation. After the discovery in the 1920s that our universe was expanding, a Belgian cosmologist, Georges Lemaitre, theorized that if the universe was getting larger and cooler, it used to be smaller and hotter, with all that energy being squeezed into a smaller and smaller area. The logical conclusion to this was that if you rewound the universe back to its very beginning, all of the universe's energy would exist in a single point in space. This singularity would be infinitely hot and dense, which makes sense. It would then explode outward in a rapid expansion, which would eventually give rise to all the galaxies we see around us. Based on that heat and explosive expansion, this idea is known as the Hot Big Bang model. So, when did this Big Bang take place? Well, to answer that, we do need to assume a few things about the universe first. 1. The universe is uniformly dense on the largest scales. This seems wrong. It's clearly not uniform. There are superclusters full of densely packed galaxies and supervoids containing not much at all. However, like stars in a galaxy, zoom out far enough and suddenly everywhere looks the same. So we assume the universe is homogeneous. As a result of that, not only is matter distributed evenly, but 2. We also assume the universe's laws and properties are the same throughout in any direction. And 3. We assume the Big Bang occurred in all locations, everywhere at once. But why do we believe that last one? The current value of Hubble's constant implies that the entire universe is expanding faster than the speed of light, meaning there is a sphere around us that we will not be able to see beyond. Past this sphere, galaxies are moving away from us faster than the speed of light, meaning light emitted by them can never reach us. Everything within this sphere is the observable universe, a term you've probably heard before. We can't see or detect anything beyond the observable universe, which is why we don't know if the universe is infinite or finite. Even if it is finite, it couldn't have an edge and would have to loop around, because, well, the universe is just that, everything that exists. What would be beyond the edge of the universe otherwise? So, where in the night sky do astronomers look to see where the universe started? Well, the answer is everywhere. Because the universe always has been the whole universe. It has just changed in size, from being very small to very big. It doesn't have specific coordinates, because it is an explosion of the coordinate system itself. Under the laws of general relativity, if these 3 things, uniform distribution, universal laws of physics, and expansion that occurs everywhere at once are true, then there is a connection between how old the universe is and how it has expanded throughout its history. With these assumptions, we can get distance and brightness measurements between objects like stars, supernovae, and galaxies. For instance, white dwarf supernovae always appear about the same brightness. If an observed supernova is dim compared to what we expect, it is because it is further away. Finding out how dim tells us how far away it is, and thus how far back in time we are looking. We can also look for fluctuations in the cosmic microwave background radiation, or CMBR. This is what shortly after the Big Bang looked like, albeit in microwaves. You can see the CMBR anywhere you look into space, assuming you have a space telescope that can detect microwaves, because Earth's atmosphere is really good at blocking microwave radiation. 380,000 years after the Big Bang, the entire universe was hot, around 2,500 degrees Celsius. Even though this heat would have emitted visible light, we can't see it because the expansion of the universe has stretched the wavelengths of electromagnetic radiation by a factor of 1,000, meaning the photons no longer arrive at Earth as visible light, but rather as microwaves. So, just like seeing those distant galaxies billions of light years away using visible light, we can see what the universe looked like before galaxies even existed by observing these microwaves. This makes this image effectively the oldest thing we have ever seen. Fascinatingly, the slight variations in the image are the precursors to the filamentary structure of the universe. We are quite lucky in that there are not really any bright sources of microwaves in the universe apart from the cosmic microwave background radiation, which means this view is a relatively uncontaminated view of the universe 380,000 years after the Big Bang. Can we see beyond that? No, not really. Before that, atoms were just becoming a thing, and light couldn't travel through the soup of fundamental particles. But the CMBR is still very useful. Comparing it to galaxy clusters we see today, there is a correlation, so we can examine the CMBR's fluctuations and use it as a basis to track the universe's evolution. Based on the expansion of the universe today, and how it did expand, we now know the universe is 68% dark energy, 27% dark matter, and 5% observable matter. But what is dark matter and dark energy? We really don't have much of an idea. However, we can see their effects. Dark energy is believed to be the driving force behind the universe's expansion, as the expansion would have slowed down by now without it. And dark matter is gravitational force we can't account for. Galaxies, and galaxy clusters in particular, seem to have a lot more mass than they should, meaning the gravitational pull is stronger. Dark matter is what must keep galaxy filaments together. We can observe its influence. In fact, we can even map out its mass distribution, like in this image. But we don't know what it is. We can't observe it. But for our current purposes, we don't need to know what it is, only what it does, to be able to work out the universe's age. So, we know the current rate of the universe's expansion, or the Hubble constant. We know how that redshifts light. We know the composition of the universe, and we know its properties. We can see how galaxies have evolved over time. We look for fluctuations in the cosmic microwave background radiation. We can use all of this together to extrapolate back to the earliest stages of the Big Bang. Using 3 different instruments, all looking at different aspects of the universe, all the answers have come back roughly the same, 13.8 billion years, with an estimated 99% accuracy. But there's another method, which has thrown a bit of a spanner in the works. While our models of the universe correlated with the evidence to a satisfying degree, over the last few decades we've increasingly realized there are things out of place too. Here is our first example of where what we think happened in the early universe and what actually did happen don't quite line up. What happens when we measure the age of stars? Certain types of stars are very short-lived, going supernova in a matter of a few million years. Others could last for trillions of years. Not that we've seen one that old for obvious reasons. In fact, following the evolution of stars, we haven't really seen any older than about 13.2 billion years old. But this does mean that long-lived stars that formed as matter was coalescing shortly after the Big Bang would certainly still be around today. The issue came through the discovery of Methuselah. Methuselah is a metal-poor star, meaning it is very old and incredibly rare, and most special of all, it is only about 200 light years away from us, which means we can examine it relatively closely. Based on its evolution, it is an estimated 14.5 billion years old, give or take about 800 million years. This means it might have disproved the 13.8 billion figure. The JWST has also been placing tension on our assumptions about the age of the universe, or at least how quickly things can form within it. In early 2025, Webb spotted its most distant galaxy yet, MOM Z14, which formed a mere 280 million years after the Big Bang is thought to have happened. While this does not contradict the 13.8 billion year estimate, it does introduce a mystery. Scientists did not believe galaxies could form in that time frame, especially one so bright and large as MOM Z14. It should have taken a lot longer. So do we really know how old the universe is? Roughly. It wouldn't be surprising to see this figure change as our technology improves, and we will have a lot more data coming in from Webb in the future. Although I don't think we'll see this figure vary by more than 1 billion years in either direction. At the end of the day, even with these other factors challenging our assumptions, the other evidence that gave us those assumptions in the first place still exist. All have to be accounted for in our final model of the early universe. But there are other challenges spotted by James Webb out at the furthest edges of the universe. In fact, when the James Webb Space Telescope finally saw the edges of the universe, we knew we had a problem. Once Webb's data started coming in as it resolved light emitted from stars 13 billion years ago, what we saw was not a sparsely populated proto-universe, where matter was only just starting to coalesce into the first, tiny, intermittent galaxies here and there. The early universe was a bustling place. It had galaxies. Too many of them. They were too bright, and the black holes we started to spot in their hearts had grown too big too quickly. As I mentioned earlier, it takes time to cook up a galaxy. Interstellar gas and dust need time to subtly come together under gravity until a critical mass is reached and stars begin to ignite. These stars live and die, and from their deaths, new stars are formed. This too takes time. Cosmologists have observed our universe and, based on what they saw, created models for how old our universe is and how quickly galaxies form, which is why the James Webb Space Telescope data caused such a crisis. Things were not as the models predicted. Fortunately, some of those problems proved solvable in the months after the data was released. For example, the brightness of the galaxies we could see through Webb. This brightness implied that there were far too many stars present in those galaxies. So many stars should have taken much longer to form, and yet there they were, fuzzy red dots at the edge of Webb's resolution. However, scientists at the University of Texas studying Webb's Cosmic Evolution Early Release Survey realized there could be another explanation for all that excess light, and counterintuitively, that explanation was black holes. If we work under the assumption that there were massive black holes in these galaxies rapidly consuming cosmic gas, then the intense friction given off by these hungry leviathans as they ate created an excess of light in their accretion disks. This explains why galaxies overall seemed brighter and were throwing off our estimates. Once you add these shining black holes, you don't need so many stars. The mass of each problematic galaxy dropped, and everything fell back into line with the cosmological model. Problem solved. This reinforced how important black holes are to our understanding of the early universe, which was in and of itself a problem, because the black holes themselves broke our models too. In particular, cosmologists struggled with the thorny question of how they'd come to be. For small black holes, known as stellar black holes, there was no issue. Stellar black holes have masses a few to 100 times that of our Sun, and we understand very well how they are formed. They are the collapsed remnants of a sufficiently massive star, and there would have been time for such black holes to form in the early universe. But scientists were struggling with the supermassive black holes, with masses tens of thousands to billions of times that of our Sun, which tend to lurk at the central point of galaxies. And due to something called the Eddington limit, there just shouldn't have been time for these kinds of black holes to have formed where and when Webb saw them. And yet, there they were, and they were numerous. Stellar black holes can grow as time goes on, provided you funnel more mass into them. But how quickly? In 1920, an English astronomer and physicist called Arthur Eddington formulated the idea that there was a limit to how quickly either a star or a black hole could grow. This was because photons carry momentum, a tiny amount, true, but enough to exert a push. This is what pushes solar sails on certain hypothetical spaceship designs, that tiny amount of momentum imparted by photons. For mass to enter into a star, it has to push against a constant stream of photons that are radiating outward, and at a certain level of brightness, not even gravity is strong enough to pull against the flow. This is called the Eddington limit, and stars that brush against its boundaries, such as Wolf-Rayet stars, bright stars at least 20 times more massive than the Sun, emanating powerful stellar winds, are just the slightest nudge away from blowing themselves apart. For black holes, you might think this would be less of a problem. Isn't the whole point of black holes that they don't radiate any light? But their accretion disks are a different story. As we discussed earlier, accretion disks around black holes can be incredibly bright, particularly around supermassive black holes, sometimes dwarfing the brightness of the stars in the galaxy they reside in. With brightness comes resistance to gravity, and black holes have to obey the Eddington limit too. So even though, given enough time and mass, stellar black holes could theoretically grow into supermassive black holes, it doesn't seem plausible that this actually explains all the supermassive black holes we see in the early universe. Simulations have been run, and although it is technically possible to grow a stellar black hole into a supermassive black hole in that time frame, it would require those black holes to be feeding at near the Eddington limit non-stop since their birth, which just doesn't happen. Black holes in real life often run out of mass nearby and need to wait to run into more, or for more to come to them. To further complicate the matter, we're not completely sure that supermassive black holes are the grown-up version of stellar black holes in the first place. Although it seems like common sense to assume so, scientists have been confused at the lack of the intermediate stage of black holes observable in our universe. To be frank, they've not cited any, at least none for sure. Supermassive black holes are common at the center of galaxies, and there are thought to be 100 million stellar black holes in our Milky Way alone, based on the number we've seen. But intermediate black holes are suspiciously lacking, with only a handful of potential candidates. You would think we'd see a lot more. Struggling for certainty, scientists began to hypothesize that supermassive black holes were instead born in some other way. Many cosmologists have been exploring the idea that because everything was much closer together in the early universe, things might have been dense enough that interstellar dust itself could conceivably have collapsed to form a black hole directly, skipping the star step altogether. If this is true, and there is some evidence to support the theory, then perhaps supermassive black holes were once capable of simply being born that size or near it right from the offset, even if such a thing is no longer possible in our more spread out universe today. But this is by no means certain. But then a black hole called LID 568 came onto the scene, and the pendulum swung the other way again. LID 568 is a very distant black hole, between 12.1 and 12.3 billion light years away. It's so far away from us that we can't see it at all using visible light. The expansion of the universe has redshifted it all into infrared ranges. But even its infrared emissions were too dim to be picked up by heavy hitters like Hubble alone. It took the Chandra Cosmos Legacy Survey's combined telescopes and the incredible resolution of the James Webb Space Telescope to see it at all. Even then, LID 568's whole galaxy is a little more than a faint, red and compact dot. But the light emissions from this red dot are revealing. X-rays given off by LID 568's accretion disk reveal that it was actively consuming matter in its galaxy's heart in a way that no one expected. You see, LID 568 crucially appeared to break the Eddington limit, and not just by a little. It was 40 times over the accretion speed limit, well on its way to having its license revoked. How is this possible? At the time, multiple explanations were given. It turns out that breaking the Eddington limit is, in fact, possible, but only for short bursts or in sneaky ways. For example, jets can help you get around the Eddington limit if all your photons are being blasted off in a single concentrated direction. All the other directions can eat to their heart's content, with no photon feedback getting in the way of a good meal. There are other possibilities. While Eddington's limit says that once the brightness of the accretion disk becomes too high, all the black hole's food will be blown away, there is a period of time before this happens where a greedy black hole can snatch at the escaping matter and potentially enter super Eddington territory. Like an overeager diner, it might pay for it later, but for a short burst, that level of accretion can occur. If this is true, it might just explain how supermassive black holes in the early universe came to exist. And if LID 568 is accreting matter past the Eddington limit, it would prove such a path to supermassive status is possible. However, there is some doubt on that point now. In a paper published in the Astrophysical Journal, two researchers, Do-Yeong Kim and Myung-Shin Im, revisited the James Webb data and realized upon closer scrutiny that dust may have been obscuring the black hole more than anticipated. This would have a knock-on effect on the black hole's Eddington limit maths, as not knowing the true brightness of the black hole makes it hard to estimate how much mass it is eating. Once they applied their new values to the equations after looking at more infrared data, LID 568 started eating mass at a much more normal rate, well within the Eddington limit's guidelines. Which means our mystery endures. If LID 568 does not break the Eddington limit, then that explanation cannot be used to account for the supermassive black hole's exceptionally rapid formation. And what of the other strange things James Webb saw? Where are the intermediate black holes that stellar black holes ought to grow into, on their way to becoming supermassive? Why are there so many galaxies in the early universe, more than our models should allow? Do direct collapse black holes, ones formed from the cosmic dust itself with no stellar intervening step, really exist? Our models might be on the right track, but something is missing or incomplete. And this is not the first time we've noticed this. Let's explore one final example. An element we use every day. In medicines, alloys, and most importantly, the batteries in our phones. One that is strangely missing from the universe, at least in the amounts we would expect. So here's the big question: where is all the lithium? Let's cover some of the basics about lithium. Lithium is a relatively simple element. It's one of the alkali metals, and for a metal is surprisingly soft, capable of being cut with just an ordinary steel knife. You might have seen it used in science experiments in school, as it reacts quite satisfyingly when mixed with water, producing lithium hydroxide and hydrogen gas. More commonly, it's used in phone batteries, laptop batteries, and in other electronic devices due to its high electrochemical potential. But the feature of lithium that makes it so important for our discussion is its internal structure. It's made with just 3 protons in the nucleus, meaning it's one of only a handful of very lightweight elements that could be created in the early moments of the universe. But it's the expected presence of lithium in the universe's beginning that causes our problem with the Big Bang model. So what do we think was going on back then? How exactly does lithium prove it's wrong? The universe's origin is murky to us, but based on what we know, at the very moment of the Big Bang, there would have been no lithium or any other atom. The very start of the universe would have been simply too hot. After that though, even just 1 second after the universe begins to expand, the picture becomes much clearer. 1 second after the universe's expansion began, the temperature of the universe dropped down to a mere 10 billion degrees Celsius, which is actually only 1,000 times the temperature at the center of our sun. This was still hot enough that matter couldn't form yet. The fundamental force that holds together the nuclei of atoms would have been overwhelmed by this intense energy. So everything would have existed in the form of radiation instead, our cosmic background radiation, which we mentioned earlier. The universe didn't remain as just radiation for long. Just 99 seconds later, it would have cooled to 1 billion degrees Celsius, and the strong force would have kicked in. The universe's first protons by then had started forming and began binding with neutrons, creating hydrogen and the 1 proton, 1 neutron isotope of hydrogen known as deuterium. Hydrogen and its isotopes, or versions of hydrogen that had the same number of protons but more or less neutrons, were the most common element in the universe. But hydrogen wasn't the only one. Everything was still filled with so much energy that the hydrogen protons frequently smashed into each other, underwent nuclear fusion, and soon created the larger, more complex element helium with 2 protons. Once you run the equations, in the primeval universe, matter was nearly 76% hydrogen and nearly 24% helium. But sometimes, very rarely, another proton would merge with the other 2 and would form isotopes of lithium, bringing the number of protons up to 3 in these atoms. By mass, this made up only 0.0000007% of matter in the early universe. But here is where the mystery comes in. By examining the spectroscopic data from stars, or by evaluating that same light as it passes through clouds of matter, we can evaluate the distributions of elements in the universe today. And what we see roughly matches this prediction. Our own sun is, by mass, 71% hydrogen, 27% helium, and 2% other heavy elements. Which makes sense, as the sun would have had time to undergo more nuclear fusion in its lifetime, slightly altering the ratios of these elements. These ratios are mirrored throughout the universe as a whole, another strong proof that the hot Big Bang model and our equations are right, and that the universe did evolve in this way. And yet, our predictions about lithium are wrong. Although the prediction for the amount of lithium in the early universe is really low, the prediction is actually still too high compared to what we see. 3 times too high. Or to put it another way, as we study the spectroscopy of primordial stars, the further away the star, the earlier in time the light would have left it, we don't see anywhere near the amount of lithium we ought to be seeing if our prediction was correct. There are further mysteries surrounding lithium. Lithium-7 is the isotope that we tend to see in the early universe. This means that a lithium atom has 3 protons and 4 neutrons in its nucleus. But there is another isotope of lithium, known as lithium-6, with 1 fewer neutron, that is meant to be much less stable and much less common than its counterpart, supposedly making up only 2 out of every 100,000 lithium nuclei. While the amount of lithium in the universe is too low, the ratio of lithium-6 to lithium-7 is much too high. Lithium-6 is a staggering 1,000 times more prevalent in the early universe than it should be. So, what does this mean for the hot Big Bang model? Is it really back to the drawing board for our most trusted theory about the universe's origins? Not necessarily. 2 possibilities exist. One that involves rewriting the Big Bang theory as we know it. But there is another explanation that might just hold the answer to it all. When faced with something like these mysteries, whether that's Methuselah stars, or an overabundance of early galaxies, supermassive black holes, or lithium, one of 2 things must be true. Either our observations are wrong, or our models are wrong. Let's consider each possibility. It's difficult to throw out the hot Big Bang model completely. Nothing else does as good a job at explaining the existence of the cosmic background radiation, or the amounts of hydrogen and helium that we see in our universe. The quantities of those elements check out almost exactly with the hot Big Bang's predictions, which seems to be too perfect to be a coincidence. That said, scientists are becoming less certain about the model as it stands. Stephen Hawking, who was once one of the leading advocates of the idea that our universe began with a singularity, later went off the idea. In his book, A Brief History of Time, he stated, "Roger Penrose's and my work became generally accepted, and nowadays nearly everyone assumes that the universe started with a Big Bang singularity. It is perhaps ironic that, having changed my mind, I am now trying to convince other physicists that there was in fact no singularity at the beginning of the universe. As we shall see later, it can disappear once quantum effects are taken into account. Those quantum effects are too complicated to go into for this video, and this doesn't necessarily solve the lithium problem or the others, even if true. But it does highlight that the origin of the universe is an evolving branch of physics and cosmology, where the full explanation of it has not yet been found. Perhaps our models will one day adjust in such a way that the lithium problem falls away, even as the broad brushstrokes of the theory remain in place, letting the jigsaw piece of the lithium numbers fit nicely with hydrogen and helium. The other option is that there is something wrong with our observations, and there may well be some grounds to this, as there was with LID 568. Because of the small amounts of lithium being discussed, it is quite difficult to see the exact amounts of it that exist in the interstellar medium once you look far back enough. The only way to probe the interstellar medium's makeup is to shine a light through it and then see which lines in your spectrograph get blocked out. This can tell scientists what elements might make up a particular nebula or dust cloud, but this gets harder and harder to do the further away the target is. Eventually, it becomes completely impossible to get an exact estimate. Instead, scientists are left looking at the spectrographs of primordial stars, which are not necessarily representative of the universe as a whole at that time. A star is a special case. Something going on inside there might be altering the amount of lithium present within, converting the lithium into something else, while boosting the amount of lithium-6, although it's difficult to guess what that process might be. If our observations could improve, and we could better measure the amount of lithium in the early universe as a whole, perhaps the numbers would come back into line on their own. Maybe the lithium problem never existed in the first place. Ultimately, no answer to how the universe came to be will ever be complete until all the available data matches the theory's predictions, whether that's lithium or other problematic elements in the universe. All these numbers have to be brought into line. There is still so much to learn about the universe's origins. I do find it incredible just how much we are able to learn and deduce about events that happened billions of years ago, back before matter itself had properly formed, using just our telescopes and our minds. That picture, the grand picture of how it all began, is waiting to be assembled. However the universe came to be, it is built on a foundation of an underlying order that allows us to unlock its principles, tease out its mysteries, and reconstruct the configuration of its individual pieces. One day, I am confident we will solve the lithium problem. And all the others too. How can we resist when the answer to our ultimate origins awaits? Some questions are just too important to leave unanswered. And I, for one, cannot wait for the day when this egg is finally unscrambled. A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape. A place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.